PFs.还是没有吗？来看一下什么东西。 Oh, okay. Are you the presenter or okay. I want just to see if I can access the presentation. I want just to check how it works, the computer before, so you have the presentation like this one. To present. Yeah. Okay. And then there is the directory with all the. I'm saying you asked me to upload in the folder, and I uploaded that. Yes. Can I just see where is the folder? I just want my list. And there is mine. Junk availability. And I need just to open it. Thank you so much. That's it.
Here for this session. Okay, hi, I'm Serena. I'm supposed to chair this session. Are the oh nice, okay, how's it going?
I need to use my laptop to share the screen, but it seems that something goes wrong.
Oh, gotcha. Okay, I'll let you figure it out.
固定的，好吧？你这块儿我还是有点问题啊。能重启电脑吗？什么？干啥？
我把
之前自己用也没什么问题吧？对，那就重启电脑。Alex 想让我去306帮忙，306一个人都没有。
OK，行。
Okay, we're having this issue with Macs sometimes.
Yeah.
So,
He
Is the-
cannot share the screen.
is the back computer also a Mac?
Yeah. You want to switch
Yeah,
around?
just try switching them. Because sometimes some of the Macs are having this issue. They can't understand.
啊，switch 吗？还是你想关机重来？重启啊，重启。重启不行，那我再 switch 好了。有 Zoom link 吗？我发你份 Zoom link 稍等。哦，有发。别急，慢慢来。往下，对，下面那个 Zoom link。你这个声音得关掉。对，关就行。哦。OK，你先加。Promote to panelist。Right。OK，现在试试。我能看见你的那个摄像头。Not working。那我来吧，你登那个 Room 摄像头 OK，好吧。Leave room 吧。
Oh, great, thanks. Okay. Yes, bridging the gap.
对。
we should have uploaded the slides to the.
So it should be good.
Yeah. But I think there's a, which speaker are you?
I'm the second speaker.
Oh, excellent.
你是没有错吗？啊，那是对，你帮我 promote 一下。然后我是 screen 试试，那会儿有吗？那是不是网络的事情？哎，有了吗？那感觉是我的问题，是我这 Mac 的，感觉是网络问题。
Well, let me take a picture. So you're.
你会 set up 那个什么吗？就是 PPT 之类的，你帮我 set up 一下，我帮你去后面把这个插上。Excuse me, yeah, don't try.
Oh, cool. Great, and then for, and you got on your side.
Yes, so we'll do that.
And one. Great, and then. Share. Move, yeah. Yeah, so. Okay. Thank you all for coming early.
OK good 吗？你让他们 test 一下，我去306了啊。OK。
I also have you. It's fine. No.
Test 一下吗？可以都打开吗？还是你想这一个一个打开
其实都可以，但可能一个打开会稍微好一点。
？OK，
但是我不觉得，但是他因为他们没有标那个，
对啊，我不知道哪一个。
那
OK，
就都打开，或者这个是 PDF，先试一下这个。
那这是怎么把它 present 呢？哦，就这样。OK，
然后上面是
好，行，那第一个就是这个，所以我就找到我自己。Figure out which one it is. Oh, I think it's this one. Okay. Now, how do we? Good. 他们能看见吗？这个 Yeah, you can share it. Yes. Okay.
然后会议里也是可以。
Okay. Maybe I'll provide this. You can Oops. That way you can see the.
Yeah. Not the. Related to the video.
Oh, okay. Then
Yeah.
Okay.
Yes. I will do my-
This one.
Second.
And then you just escape to the.
Then you upset. Okay. Okay, great.
Okay, I think we're good.
So-
Okay, I think we're ready to get started. I don't see another mic here, so 10:35, yeah. Great. Okay, so welcome to Responsible Web Session 2 on ecosystems. I'm Serena Wong. I'll be chairing this session and kind of just, bringing speakers on and off. And our first talk will be from Emmanuel Papadogiannakis. Did I do that right? On Welcome to the Dark Side, Analyzing Revenue Flows of Fraud in the Online Ad Ecosystem. So thank you.
Great. So, hi everyone, good morning. Welcome to the session. Welcome to the dark side. Today we'll be talking about the online advertising ecosystem and some types of ad fraud. So, a very quick outline. I will first talk about the motivation behind our work. I will then give you some short background information and discuss the types of ad fraud that we studied in this paper. And finally, I will close with a web service that we built to address those issues and a short conclusion. So, the online advertising ecosystem is a very profitable market. It is a market that has already surpassed the 500 billion mark, and it's expected to reach $1 trillion soon. So there is a lot of money at play. Now, because it is a very big and complex market, it is also vulnerable, right? And people are always trying to find ways to steal money out of this ecosystem. This is what we call ad fraud. Now, ad fraud doesn't always look like some hackers hiding in dark basements trying to steal your data and your money. Sometimes bad guys only need to misuse the rules. There have been some transparency standards in the advertising ecosystem that try to stop ad fraud, but bad guys unfortunately always find ways to abuse them and generate money. So the main questions of this work are basically how efficient are these advertising standards and how are objectionable websites able to abuse them and funnel money into low quality or even sometimes illegal websites. These are the questions that we will answer today. But before we do so, let me give you some background on the advertising ecosystem. So this is one of the advertising standards already implemented on the web that attempts to stop some form of ad fraud. It is called ads.txt files, and these are simple text files which basically say which advertising networks are allowed to sell the ad space of a website. So if you see the example here, we can see that BBC, the news website, has authorized Google and OpenX to place ads on its website, right? to sell its ad space. We can see that at the bottom right. Now, another file that increases transparency is called sellers.json. This file is published by ad networks this time and basically lists all the sellers of ad space that work with the platform. It basically says, here are the websites that I work with, and this is where I place my ads. So again, if we see the same example, we can see that Google has approved BBC, the news website, to get Google Ads. Now, you may have noticed that these files use identifiers. These identifiers are used in both files and basically uniquely show the advertising account, your advertising account. It basically identifies the wallet that gets the money from the ads that you display. These are the accounts that we study in this work. So now that we have a brief understanding of the two advertising standards that dominate the advertising ecosystem, let's see how we attempt to reconstruct the supply chains in our work. So let's start with an example. Let's say that I own a website that publishes fake news content, right? I call it fakenews.com. Since I have a lot of visitors, I want to make money out of it, right? I have many visitors, I want to make money, that makes sense. So my first idea would be to place some ads on my website. So I will go to Google, I will create an advertising account and say, you know what, give me some ads to place on my website. The thing is that most likely I will get rejected because Google and multiple other advertising networks do not really allow misinformation for their advertisements, so they will reject me. Now, since I got rejected, what if I get in touch with the owner of a different website? Let's call it bookreviews.com. This website is a legitimate one. It has already been approved in the past and it gets Google Ads. What I can do is that I can use this guy's advertising account, use it on my website, and also get ads. This is what we call pooling. We basically pool the advertising space from different and unrelated websites under the same account. Now, since the other guy was kind enough to lend me his account, I will most likely share some of the revenue I generate, some of the money with him. So now everyone is happy. I get money from ads. He gets some money from the portion of the money that I make, and everyone is happy. Everyone except Google and the advertisers that basically gave money to a fake news website. Now, one could say that since I own a fake news website, it will be difficult for me to find someone else to work with and share his account. That is correct, but unfortunately, there are some advertising intermediaries, some middlemen that facilitate this operation, that facilitate pooling. They manage multiple websites and bring people together under the same account. So they are the middlemen that operate different websites. These middlemen are often called intermediaries or ad brokers or ad syndication platforms, sales houses. You might hear them from with different names. So what we did to discover pooling on the web is that we started from 7 million websites and try to find those that use and share an ads.txt files. When two different websites use the same advertising account to display ads, this is what we call pooling, and they form a pool. We found that this is a very common practice and that a lot of publisher IDs are being reused across multiple websites. There are 185,000 cases of websites using the same advertising account to display ads. And there are some ad networks like OpenX, Index Exchange, and PubMatic, whose identifiers are almost always used for pooling. Even for Google, 1 in 4 advertising accounts are used in multiple websites. Now, I should point out here that pooling your websites under the same account is not necessarily a bad thing. I can own 2 different websites and use the same account to show ads in both of these websites. This makes sense because it is easier to maintain. The problem is when unrelated websites use the same account because it is not clear where money flows to. This is what we call dark pooling on the ad ecosystem. And unfortunately, we discovered 15,000 such cases. So I have a very short example here to explain why dark pooling is indeed bad. Let's say that some of you are, I don't know, an advertiser, and you buy ad space through a reputable ad exchange, and you expect your ads to appear on high-quality websites. However, behind the scenes, there's a shady network of misinformation websites that are using the same advertising account and basically hide the real source of ad inventory by mixing good websites with bad websites. This means that you, as an advertiser, might have your ad appear next to misinformation and basically fund fake news without wanting to do so. And unfortunately, we found thousands of such cases with dark pools of either misinformation or piracy websites. Now, let's take a closer look at the middlemen, the hidden intermediaries. When you create an advertising account, you need to specify if you are a website publisher, basically the guy that owns a website, or a middleman that manages the websites of other publishers. And advertisers usually prefer to work directly with publishers because they know where their ads will appear and their money is not spent by middlemen. Unfortunately, we found that some intermediaries, some middlemen, pretend to be website owners and they basically get ads as owners and then distribute them and send them to other websites. So they mask the role and obscure the real source of ad space. You can see that these intermediaries basically manage the ad inventory of a lot of websites and obscure the supply chain of advertisements. So this makes it hard for advertisers in the end to know where their ads will appear. Will they appear in a good website or a bad one? In our analysis, we found 33 such cases where advertising middlemen are pretending to be publishers and then push their ads to low quality or even objectionable websites. One such example is Next Millennium Media, which is infamous for following this practice. And we also did a historic analysis and found that they keep this behavior over time, so this is not a mistake. With this practice is that these middlemen can get ads and then give them to their own clients, right? The intermediary gets the ads and then forwards them to their clients. These clients are often objectionable websites, and you can see that we found almost 200 misinformation or piracy or even illegal gambling websites. So these intermediaries facilitate ad fraud and fund objectionable content. Now, to address all of these issues that we've discussed today, we built a web service that attempts to increase the transparency of the advertising ecosystem, and it can help stakeholders understand the actual relationships between websites, middlemen, and advertising networks. I have a screenshot here that just showing that you can look up various things and understand who works with who and what information they share and how money flows to websites. So, to recap, today we talked about the advertising ecosystem and how complex and fragile it is. There are some advertising standards, transparency standards that were supposed to bring more transparency, but they are not properly used on the web. Bad guys manipulate them, and money that should go to trustworthy website owners, publishers, actually ends up on low quality websites. And there are some advertising intermediaries that facilitate these operations. The one thing that I would like for you to remember from this presentation is that transparency standards are not properly implemented on the web, and this allows bad guys to exploit them and generate ad revenue from objectionable content. Thank you very much. Thank you for your attention, and I'd be happy to answer any questions. Oh, please. Yeah.
Yeah, so is it done in programmatic or you guys were exploring those ad networks like Meta has or Google Ad Network? In other words, is this a real problem for big players like let's say Meta Ad Network? Or it's more like a programmatic game where you can, inject lots of intermediates and make money from there?
We are talking about programmatic advertising. So these are operations done in milliseconds and often.
There's Meta, and Meta is also programmatic, but they have placements mainly in their own website.
No,
They have ad network as well, so my question is whether that ad network have all these issues in there as well.
No, we didn't study that. We studied programmatic advertising in terms of open RTB and advertisements showing on publishers' websites. So yeah, our findings focus there. That's why there are so many middlemen involved in the supply chain that obscure the actual source of ad inventory. Yeah.
Up here.
Yeah.
I think it'll show up on the Zoom better.
Yeah, so how do you detect that a website is a misinformation website? Or is it based on the domain name, or do you also look into the actual content of the website?
That's a very good question, very good. Classifying a website as misinformation is a very hard problem, right? And there are so many organizations around the world focusing on this problem. That's why we basically outsource it to these organizations. We used the data set of Media Bias Fact Check, a very credible international organization, as well as previous academic papers, and accumulated a list of misinformation websites. So we did not classify them as well. We leave it to the experts.
Yeah, just to follow up is that, again, the same issue is the domain might be credible, but they can still be pushing conspiracy theories or.
Yeah, these organizations like Media Bias Fact Check are actually checking the content of the website.
Okay.
They don't focus only on the domain name, so they read the articles and they try to dispute them using proper fact-checking methodologies, right? So if they push conspiracy theories, then they will be flagged, and then we study them as misinformation content.
I think we're just in the interest of time, we have to move on
Yeah.
to the next speaker, unfortunately, but please, yeah, continue to take questions offline. So let's thank our speaker.
Thank you. Thank you.
Okay.
The first one.
The first one, excellent. Okay, good. Yeah, of course, I got you. Okay, so our next speaker is Ahsan Zafar, speaking on assessing compliance in digital advertising, a deep dive into acceptable ad standards. So can't clap well.
Right. Sorry.
I'll say that to you when you have 2 minutes.
Perfect. Good morning, everyone.
My name is Ehsan Zafar. I'm a fifth-year PhD student. I work with Dr. Anupam Das at North Carolina State University. The title of my paper is Assessing Compliance in Digital Advertising, a deep dive into acceptable ad standards. As we already know, online ads are what sustain the web as we know it today. They create revenue streams for web publishers and content creators. And unfortunately, we've seen in the past a surge in the spread of distracting and intrusive online ads. I'll talk more about some of these ad formats. But as a result of this proliferation, users have, in retaliation, adopted ad blocking mechanisms. These come in the shape of browser extensions or other privacy-enhancing technologies. But the point is to use them and to get rid of all the ads that you see on the web page. This has created a problem for publishers, for content creators, as they have resulted in a revenue loss for them. And this has subsequently led to a downgrade in the content of the quality of content and availability of that content. Just to set the mood, you might be familiar with some of these ad formats that are very annoying, that can distract you from your browsing experience. Sticky ads which persistently occupy your screen space. Autoplay video ads which will catch you at surprise when you land on a page and the autoplay video ad will start playing automatically. Or the overlay ads which will hinder your ability to interact with the main primary content. And expanding ads, again, a distraction. This is an example of an oversized image ad found on a very popular news website. It's taking a huge chunk of your screen space. This is another ad which occurs on the landing page, and it's an autoplay video ad. So as you land on that page, the video starts playing, and it creates distraction. So we have this problem where users want to get rid of the ads, and it's hurting the revenues of these online publishers and content creators. Emerging out of this problem, ad standards have been introduced, which basically strike a trade-off between protecting the revenue stream of website owners and protecting the user experience. And primarily, these ad standards define restrictions for what kinds of ads can be allowed and what can be disallowed. So there are two leading ad standards today. The first, acceptable ad standard, and the second, better ad standard. Now, in prior literature, better ad standard has already been studied. Its enforcement has been examined. In this paper, we focus on the acceptable ad standard, which is the leading ad standard used by 300 plus million users. And it specifically places constraints on size, placement, and distinction of the ads. Additionally, it also limits what ad formats can be allowed and what are prohibited. So for ad publishers who want to protect their ad impressions, they can place a request with the enforcers of acceptable ads and create an exemption for their ads on particular domains. So these constraints that I've talked about in the previous slide include size restrictions. So when you land on a web page, the total area that all the ads in that frame occupy should be less than 15%. When you're scrolling, the total area should not exceed more than 25%. The ads should be very distinct. So clear labels that specify that this is an ad, whether it's sponsored, ad, advertisement, whatever, there should be some text label that makes some distinction for these ads. And finally, placement. So the ad cannot overlap the primary content. And these are some of the ads deemed as prohibited, deemed as intrusive. and are thus forth prohibited under the acceptable ad standard. So expanding ads, pop-up, pop-unders, animated GIF ads, video ads. So how are these standards enforced? So they're enforced through the browser extensions. And let me talk about how an extension typically works. A user visits a web page, fetches the document from the server. It's a pre-rendered web page, so the browser extension, which is facilitating the ad blocking, is going to monitor the resources that have dynamically loaded on that web page, pre-rendered, and it's going to remove the ads based on a list that identifies those ads, a regex-based list. So in the first configuration that I'm showing, we're not allowing any ads. So you see that these ads are removed. Now, in the case of a user who has subscribed to the acceptable ad standard, an additional list will be added to the browser extension, which will make sure that all those ads which are deemed as compliant are kept and all the other ads are removed. So this paper is focusing on examining the enforcement of acceptable ad standard, again used by millions of users. And in this regard, we have leveraged a two-crawl ad detection framework to create a data set of allowed ads. We examine these ads on those partner domains which have agreements with the acceptable ads that they will show the compliant ads. And we design 6 heuristics for ad formats that are prohibited. And based on our analysis, we discovered that there's a significant non-compliance of ads found on those partner domains. As such, we highlight the design flaws in the enforcement of acceptable ads. And finally, we propose some recommendations and demonstrate that those improvements to the enforcement can yield an improved enforcement of acceptable ads. So this is our data collection pipeline. We're targeting 10,000 most popular websites which are partnered with the acceptable ads. We visit the website and we inject a monitoring script at the head of the document. So that is going to monitor all the ad resources within that web page. Based on the configuration, in the first crawl, it's going to remove all the ads. And in the second crawl, it's going to only keep those acceptable ads. Taking the delta based on the X path will give us the allowed ads or the acceptable ads. So we study the prevalence of these non-compliant ads. In this first instance, I'm showing you all the ads that were displayed. So we have not. We have allowed all the ads to be rendered on the web page, and we see that among these 6 categories, in total, 53.4 thousand non-compliant ads were seen. But these are for overall all the ads. But what happens when a user who is subscribed to the acceptable ads, how does that user see these ads? So in an ideal setting, you should have the second column, all the numbers should be 0 because that's how realistically we want to enforce it. But unfortunately, we saw that there were still non-compliant ads being shown. So the major categories of ad formats were oversized image ads and overlay ads. And about 10% of the domains that we visited were showing violating ads. We move forward to study the main causes for these non-compliance. And there are 2 primary reasons for why these non-compliant ads showed up at the first place. So first, there was the presence of over-permissive rules within the exception list that creates exception for these ads. The rule that I show in this example creates blanket exception for an entire domain. So all the ads will be shown on that domain by that publisher. And secondly, we observed that there were persistent ad frames that were persistently showing violating ads. So in this metadata that I've shown on the left side, our crawler gathers this telemetry data, this metadata, and it shows you the ad source, the filter rule that was applied to create exception for it. And we see that over multiple iterations, we keep seeing the same ad publisher showing autoplay ad. So after identifying these problematic rules, we purge them from the exception list and demonstrate that you can improve the enforcement of acceptable ads. So we found that initially, while there were 937 violating domains, that number reduced to 634. So almost 32% improvement in reducing those violating domains. And other two major categories of violating ads, like oversized image and overlay ads, also increased by more than decreased by more than 20%. So we recommend some changes be made to the enforcement of acceptable ads, more fine-grained rules that target specific ad formats should be designed, and over-permissive rules should be removed as they are against the spirit of these ad standards. And finally, persistent offending partners should be penalized. We have communicated these findings and these recommendations to the relevant company, IO, that enforces these standards. And they have accepted most of our samples and in contributing to that effort, we have open sourced our framework, which can be found if you access this QR code. If you would like to contribute or if you would like to learn more about this project, please contact us. And thank you for listening. Yeah, any questions? Yes, please.
Currently, compliance for you is mostly about how the ad is presented, right? Size, autoplay, things like that. Not the content of the ad itself.
No, these standards have nothing to do with the content.
Okay.
Yeah.
So, I mean, content can also be violating some compliance requirements, right?
Content?
Yeah.
Those different standards will be handling those kinds of violations then.
Okay.
These strictly have to do with the intrusiveness or the annoyingness of the ads and their ability or their potential to distract you from your experience.
Yeah. Okay.
So the standard.
A follow-up on this question. Doesn't the content of the ad also interfere with the user's I don't know, engagement in the website? So if the content is flashy or adult content or something violent, doesn't this fall under the acceptable ads standard?
It does not. It does not. Yeah. Google and other Meta, they have their own policies on content monitoring, but acceptable ad at this stage does not consider. Yeah.
Yeah. Right.
There, I have one more question.
Thank you. Were you able to benchmark your results with the other standards? I don't know if there were, you mentioned two standards at the beginning, right? Are they comparable somehow? Could you benchmark your result with the other, or they're two separate environments, let's say?
They're very separate in the sense that the better ad standard, it is enforced upon, and it is adopted by industries. So Criteo, Google Ads, those will enforce those. Whereas this is more on the client side. Their specifications on the ads also differ. So there are some intersections, but mostly I would say they are different. I would be happy to refer to you to the study that has done the other ad standard. Yeah.
So much.
Thank you.
Do you know which number yours is? Cool. Okay, our next speaker is Teresia Rampizella. Did I do that right? Okay. Speaking on joint evaluation of fairness and relevance in recommender systems with Pareto Frontier. So,
good morning, everyone. My name is Teresia, and I'm presenting our work on how to evaluate fairness and relevance for recommender systems. And this is joint work with my PhD supervisors. So this work is centered around these two questions. So first, what is the maximum achievable fairness and relevance based on whatever data set that we have? And the second is how close is the model performance to an ideal balance of fairness and relevance. So in this presentation, we are going to walk through the answer to these two questions. But first, let me give a bit of background, especially because this work is a bit different from the previous two talks. So recommender systems are systems that can match items to users such that the recommendations are first relevant to the users, which means that the users like the items or find them useful. But we also want these recommendations to be fair to the items. And this fairness has a lot of definitions. We work with one of those fairness definitions, and that is fairness means that each item get recommended to the users for a similar amount of times. So let's go through an intuitive example of what individual item fairness means in recommender systems. And in this example, we want to recommend 2 items from a pool of 4 items to the users. So here are the 4 items in the dataset. And in the first case here, we can see that there are 3 out of 4 unique items that get recommended or get exposed to the users. And in the second case, we have all 4 unique items exposed to the users. And because there are more unique items that are exposed in the case 2, so here case 2 is fairer than case 1. So now back to the evaluation part. Here we want to evaluate 2 aspects, fairness and relevance. And suppose that we have the scores from 3 models. So we have model A, B, and C. And then if we measure fairness and relevance separately, assuming that both fairness and relevance measures range between 0 and 1, then we will have model A with the best fairness, and then model B with the best relevance score. But then model A, even though it's the best in fairness, it is the worst in terms of relevance. And model B is sort of the other way around. It's the best in relevance, but has the worst fairness. So, okay, maybe deploying model A is not a good choice, but models B could be. But maybe we want something that is a bit of balance between these 2 aspects. So that's the goal. We want to have a model that is balanced in terms of both fairness and relevance. So then from this example, maybe we can sort of think or see, okay, maybe model C is sort of the best in terms of both. But how do we come to that conclusion? So maybe one way to arrive to that conclusion could be reached by averaging, or maybe not. Because if we average the fairness and the relevance scores, then we would have the model A having the best average score. But then averaging in itself is also problematic because of 2 reasons. Because the input to the 2 measures may be different, and then the measures may have different scales or distributions. And then because of these 2 reasons, it may lead to incorrect conclusions. So now back to the first question. What is the maximum achievable fairness and relevance scores based on the dataset composition? And the way to quantify this is by generating this thing called the Pareto frontier. And what this Pareto frontier means is that given a certain level of relevance, that point is the maximum achievable fairness based on the test set. So it's like a set of different solutions representing different trade-off between fairness and relevance. So then if we take the distance between our model score and a point that we choose in the Pareto frontier, then we can see that model C is the best in terms of the closest distance to this reference point. And here we are using, let's say, Euclidean distance. So this should answer the second question, which is how close the models are to an ideal balance of fairness and relevance. So the next question would be, how do we generate this Pareto frontier from the test set of the data sets? So we contribute a new algorithm, which we call Oracle to Fair. The full technical details are in the paper, but we will walk through the intuition and the main idea of the algorithm here. So we start by creating maximally relevant recommendations, and we do this by recommending items in the test split. So if we recommend items in the test split, then effectiveness or relevance would be maximum because all the items are relevant to the users. Then we iteratively replace the most popular items in that initial recommendation with the least popular items. And in this way, we increase fairness, but then maybe we sacrifice relevance a bit. So that's why fairness goes up, but relevance goes down. And at the end of this process, we will have the fairest possible recommendation. So for each of these steps, we actually compute all fairness and relevance measures. And for each iteration or for each replacement, we keep computing these measures. So each of, actually this line, this curve, consists of many points, like 1,000 points or something. And that represents all possible fairness and relevance scores that can be achieved with the dataset. So next we can compute the reference point. And we do this by selecting a parameter alpha. And alpha controls the relative position between the starting and ending points. So alpha equals to 0 would mean that we only consider relevance. And alpha equals to 1 would mean that we only consider fairness. Then after that, we can use this reference point to compute the distance between the model and the reference point as the distance to Pareto frontier, or DPFR, which is the evaluation approach that we propose. And then we also have some experiments. So we use 6 publicly available datasets with various sparsity, size, and from various domains like music, video recommendation. But these are all interaction datasets, so they are clicks or ratings. For recommendation models, we use 4 models ranging from baselines like KNN-based model to deep learning-based. And we also use 3 different fair re-ranking strategies. For evaluation, we use 2 types of measure. First, the single aspect measures, and we have 6 relevance-only measures and 5 fairness-only measures. Then we have measures that can quantify both relevance and fairness. So there are 5 existing joint measures of fairness and relevance, which quantify fairness with respect to relevance. And we also have average as another joint evaluation baseline, which is just the average of the relevance and the fairness score. And lastly, we also have DPFR, which considers also both relevance and fairness. And because DPFR is used with existing relevance and fairness measure, we try a lot of combinations of these relevance and fairness measures. So all 30 of them. So let's walk through some of the most interesting findings. First, we compare the DPFR and the single aspect measures. So for all data sets and for all measure pairs, we found that the best model based on DPFR is always different from the best model based on the single aspect measures. And almost half the time, the best model as per DPFR is actually different from the model based on the fairness measures. So we cannot really use this single aspect measure to as a proxy for DPFR. So another question that could come up would be, can't we just use the existing measures to reach the same conclusion as DPFR? So we also look into that, and we compare DPFR with the existing joint evaluation baselines. And to do this, we compute Kendall-Stall agreement between the ranking of models given by DPFR and by the joint evaluation measures. So this is the ranking of models from the fairest to the unfairest. And the idea is that if Kendall-Stall is at least 0.9, then we consider the two rankings are equivalent, and then these two measures have the same conclusion. But then we found that existing measures that jointly quantify fairness and relevance, they do not consistently rank models equivalently to DPFR, so they are not a reliable proxy for DPFR. And then we also look into comparing DPFR and averaging the fairness and relevance score. And we do this by counting the percentage of times the best model based on averaging differs from DPFR. And the best model based on averaging differs from DPFR up to 83% of the time. And we can see here that there is a huge range of variability across datasets. So between 0, so it means 0 disagreement, to 58%. So this means that if we average fairness and relevance scores, then we cannot guarantee that we can get the same result as DPFR. So in summary, we contributed DPFR, a new Pareto optimal based evaluation approach to evaluate fairness and relevance jointly. And we do this by measuring the distance between the model performance to an ideal balance of fairness and relevance based on existing measures for relevance and for fairness. And the approach is model agnostic, which means that it is based on the test set competitions, and it can be used with any models as long as we do offline evaluation, which has a test set. And then we also have provided the link to the paper, code, and another related paper where we did a deeper investigation into joint measures of fairness and relevance. And we have an extended version of that paper coming soon. And thank you for your attention.
Expert in this area, but this also reminds me Skyline optimization, right? Which is a multi-criteria optimization. Here you have fairness and relevance, but what if you have multiple criterias? That you want to optimize for?
For example,
how does it compare to your method, and why did you choose Pareto and only these two?
which optimization method again?
Skyline optimization?
I'm not
You've
familiar.
never heard of it.
Sorry.
We can follow up later, maybe.
Yeah,
if you don't.
but what we are trying to do is not to optimize the models, but we generate this Pareto frontier just as a like ideal benchmark. So it's not the model.
Yeah, Skyline is also an optimization algorithm to balance between, let's say, price and something else. Yeah.
Yeah, I'm not aware of this, but we can maybe chat after.
Yeah.
For this actually experiment, which kind of models you used? I mean, you contribute this evaluation approach, but what models you used for do this evaluation?
So do you mean the recommender models?
Yes.
We use combination of memory-based model like item K and N, but we also use deep learning-based models like BPR, NCL, and I think multi-VAE. So combination of both.
Okay, thank you.
Okay, thank you so much. Yours is. Nice. Okay, great. So next we have Eduardo Serra. Speaking on, everybody's just been saying their own title, so I'll let you just say your title instead of me.
Thank you, everyone. Today I'm going to talk about a paper that was accepted to TWeb and is about to estimate joint credibility of news user and publisher with what we define the role relational graph convolutional networks. This is a joint work with other co-authors, Francesca Spezzano, Jason Duran, and Anna Shrestha. The goal of this paper is try to estimate this combined credibility score that depends by all the interaction between user, news, and publishers. Compared to the related work at the time of publication of this kind of paper, mostly they were considering just at least maybe two kind of entity, maybe user and news. And also they did not, they always consider a kind of granularity that is binary, fake versus real. What we try to do is to combine the two and obtain a kind of general definition of the credibility score that depends by all the kind of information and to consider not just a binary score by itself, but some other degree and granularity. We have several related work, Defend and others, and SureFact, and all, not all are able to predict score for users, news, and publishers. Probably the only things is Markov random field that was applied to try to do the kind of approach that was applied to do this kind of work in combination. And in general, if we want to summarize the related work at that time, mostly the things is that they don't combine and they don't use multiple granularity and they assume if they in the case of Markov random field that the nodes are kind of homogeneous and not specialized with the type. This is our information ecosystem. We have this graph with user, publisher, nodes. We have the publisher that publish a news. We have the news that is shared by a user, and we have users that follow other users. And we try to combine all this information together. And we have, we consider specific node type that are essentially function mapping each node with the role. Just to be clear, I'm saying if there is a node that represents a news, the role is the news or the publisher as a role publisher. And after that, kind of different relations. And this is the kind of graph. Our approach is essentially based on this idea that we have each node with different roles, then each node has specific features that characterize that kind of role. And then one first things that we define is a way how to homogenize the different features for different roles. Then we decide to use this kind of mapping layer that we call heterogeneous feature layer mapping that try to transform all the features from different kind of node in a common space. And at that point, we can process this kind of things as feature in the same space. After that, for each role, we are going to assume that exists a specific relational graph convolutional network, then at least operator. And then at that point, we have for each role a specific relational graph convolutional network that will aggregate the information of the neighbor of that node, and so on. What we did, we then composed our kind of supervised task with the loss that considered the cross entropy for each kind of role nodes. And at that point, we just train the network, the graph neural network, the role relation graph convolutional network. And from that, instead to use directly the classification, we extract the features of the node, and then we use these features directly with other classification approach. Specifically, we use random forest as classifier after that. And here there is some math formulation of the final role relation graph convolutional network. And the first stage, the stage at 0, the level 0 has this kind of linear transformation that essentially map all different kind of features in the same space according to the specific role of these features. And so on, sorry. For features, we consider different kind of feature again from role, and essentially we combine the features that were proposed in the past by different other work for each specific role. Here we have a kind of summarization, and in terms of data set that we use in our experiment, we have, first of all, politic fact data set that is not essentially collected by us, exists, and usually as news for, as information, binary information for news, if they're fake or real. They have user information that can be fake, that can be considered spreader of fake news or spreader of real news or something mixed, and then we have to relabel. And after that, we connected this with extra information with essentially the media-based and fact-check website to understand the publisher information. And then we obtain this kind of data set with all the information that they declare. Apart from that, our team collected another data set of information that we call Politic Fact 2021, that refer, of course, from the year 21. But at that point, we use a different granularity for news and the user. Essentially, the news in the PolitiFact, actually, in the PolitiFact website, there is more than just the binary granularity. And the original PolitiFact just binarized that when they released. And then we recollected again, and then we have the kind of multi-grain distribution information, and this is more or less the things. This data set we made available through GitHub. You can find in our the link in our journal of the web. And here some experiment setting, some base things, some kind of parameter setting that we use. The dataset is highly unbalanced, that we use the phone score to measure the accuracy of our experiment. We did the 5-fold cross-validation and so on. These are all the baselines that we use. And again, we have the last one that is the Markov random field. And here we have some preliminary result. Of course, as I told you, not all the work are going to generate a score for each role. Then you have empty spot in this table. But what we can see is that at least for our approach, RGCN is able to essentially have an improvement respect to all the related work in the specific context where they are working in both the data sets. And we did some ablation study by removing relation in this graph, right? And then you can see that really having more relation or more information helps the system in a better prediction. And after that, we did just some difference between our approach, that is raw relational graph convolutional network, versus just relational graph convolutional network. To apply the relational graph convolutional network, we enlarge the space of the feature in the way that we have a uniform space for all the. I'm saying we just put blind spot 0 for according to what is the kind of specific set of feature, and we concatenate it. But essentially, you can see that there is some increment of performance when we use our approach. And what we did, we consider an approach that we create an approach that merges all this information, has the ability to consider a multi-granularity things, and we defined the role RGCN, and our experiment showed the efficacy of this approach. Thanks.
So if I understood correctly, the graph is fixed, right? But what if there are new emerging content?
Well, I'm saying that this is done with the graph neural network.
Yeah.
I'm saying it's able to do inference. Then if we change that graph, we expect there should be some kind of difference, but we didn't test how it works.
That's.
But do you need to retrain the
No,
model?
I say in theory, no. In theory, you can do the inference. Makes sense?
Inductive inference, yeah.
But how it works with that step,
Okay,
we
yeah.
don't know. But in theory, it's better.
Yeah. Thank you.
Thank you for the presentation. Can a node in the graph have multiple roles? Can a node be both a user and a publisher?
In theory, we can do that. I'm saying at least for ours defined, right? We can create this kind of new role that is a combined role, and we can manage it. We didn't have the data, or we didn't.
So when you did this formulation, what you had in mind was basically news websites and visitors that consume news. So it cannot be can it be applied to a social network type of thing where a user can also produce? Yeah.
Yes, the only thing is that to have the ground truth of that, I'm saying is little bit predefined that we, yeah. I think the model is flexible at the way that can do what you're saying, but the data is another matter, another story.
That makes sense. Thank you. Thanks.
I think we have time for another question. Okay, thank you. This one, right? Okay, so our last speaker is Xuan Wu on, yeah, I'll just say adoption of recurrent innovations, a large-scale case study on mobile app updates. So thank you.
Thank you. Hi everyone. My name is Xuan Lu, and the work I'm presenting today is a joint work with. So I'm from the University of Arizona. This is a joint work with Peking University, University of Maryland, University of Michigan, and Alibaba Group. Okay, so first of all, does anyone here know the diffusion of innovation theory? All right, it's fine. So this theory seeks to explore how, why, and at what rate new ideas and technology spread. So what is an innovation? Innovation is an idea, practice, or object that is perceived as new by an individual or other unit of adoption. So this thread of theories and its variations has been studied for decades since Rogers' classic book Diffusion of Innovation, first published in 1962. The theory and its variations have been widely applied across multiple disciplines. And the plot here shows the basic idea of how innovations are diffused according to the theory. So we can see this curve shows the diffusion pattern, and the adopters of the diffusions are categorized into 5 different groups according to how soon they adopt the innovation. And this curve shows the market share of the innovation, right? We can see an increasing trend here, okay? So most of the works in this field has been focusing on single innovations, such as appliances, telecommunication services, digital imaging technologies, and so on. There has been limited work investigates successive innovations. So successive innovations means there are different generations of the innovation, and the studies have investigated how the different generations of innovations are adopted by users. So examples of successive innovations include integrated circuits, like IBM mainframe computer, and so on. And this kind of innovations usually update on a yearly basis. And this kind of innovations are basically distributed with a career of physical products. And this kind of work, one main challenge in this kind of work is a lacking of user level data. So there's limited analysis on the user level. Okay. So our work focuses on recurrent innovations. So what is recurrent innovation? This is a special group of successive innovations that update recurrently with much shorter intervals between updates. Let's say like mobile apps, right? You can assume a mobile app can be updated in a few days, in a few weeks, right? And like OS or mobile OS, browsers or programming languages, like we can see Python 3 can release 2 versions each month, right? So a typical example is still, the mobile apps. We can say it is very simple to install or use an app on your mobile phones. Like you can just adopt one version, one update of a mobile app by merely clicking on your phone, right? So compared to the traditional innovations like the single innovations or successive innovations, why do the recurrent innovations can be adopted in a much faster frequency? So in addition to the resources invested in creating this kind of innovations, the distribution channels like the internet and web services have been contributed a lot to the efficiency, in distribution of this kind of innovations. And we can see a very different aspect that how users use and interact with the innovation is more important, more significant than just buying or installing it. Okay, so compared to how these recurrent innovations have been impacted people's lives and work, how recurrent innovations are adopted is largely unknown to innovation creators, stakeholders, and disseminators. So our first question is, do existing theories of the innovation distribution still hold? So using a public data of the release date of the Android OS, we can see very different patterns here. So we can see the market share increases of the past versions of Android OS slows down and reverse after new version releases. So this kind of patterns and the potential interaction between the versions cannot be explained by the traditional diffusion of innovation theory, including the single innovations and the successive innovations. Okay, so from the pattern, we can also observe that the diffusion process of an innovation can be affected by its previous and subsequent updates. And our work, as far as we know, is one of the first systematic analysis of the diffusion of recurrent innovations. So here's our data set. We studied the recurrent innovation in the context of mobile apps. And in our data set, we treat a mobile app as a technology and the different updates, different versions of the apps as the innovations. And the data is composed of the app usage behaviors. So this data is a 5 tuple, including the user identifier, which is anonymized, and the app identifier, which is also anonymized, and the app version, the start time and the end time of the user using this app. And this data set spans from August 2018 to June 2019, and it includes 17 million users, more than 200,000 Android apps, and more than 700,000 app versions. So here we define the adoption of an app version by the time a user first uses this version. Okay, so let's first revisit the diffusion process in the classic innovation diffusion theory. So this is a bell-shaped time of adoption curve, and the adopters are categorized into innovators, early adopters, early majority, late majority, and the laggards. Okay, so for recurrent innovations, will this adoption curve still hold the same bell shape? So let's dive into the adoption curves of the mobile apps. So first, we look at the new adopters. Which the new adopters means that they have never used any version before the release of a certain version, right? They are new users of this app. We can see that the adoption curve is pretty much similar to the bell-shaped curve of the traditional adoption curve. And you can see when a version releases, there are some users immediately adopt this version, right? And it takes some time for the majority to come, and we can see some jitters, possibly due to seasonal factors or promotions of the apps, something like that. And we can see there are some late majorities and the laggards. And even though new versions comes out, there are still, users started to adopt the older version. But when we take a look at the recurrent adopters, the pattern is quite different. So what are recurrent adopters? Recurrent adopters, they have used a certain version of the app before, right? And when the new version comes out, they adopt it again. We can see a big difference here. Like when a new version comes out, a significant proportion of the existing adopters will immediately adopt the new version. And we can see a very strong right screwed pattern here. So when a new version comes out, when a newer version comes out, the adoption curve of the recurrent adopters slows down, right? And it finally reaches 0 when newer and newer versions come out. So by comparing these two plots here, we can see there's at least one new type of adopters in recurrent adopters, right? A large proportion of users, they promptly adopt the new version. And these users may be the fans of this app, or they use app really very frequently. So these are the plots of the cumulative adopters of an iteration, and we can compare this with the cumulative market share of the single innovations. So we can see. So here we use two examples. One is a video app, another is a fitness app. And we can observe the consistent patterns of the adoption curve across different versions and different apps here. So upon release of a new version of an app, the number of the adopters increases sharply, right? And it reaches the peak when a subsequent version is released. And then it declines fast at first and at a slow pace after that. So this steep slopes in both the increasing and decreasing phases follows the release of a new version are clearly driven by the recurrent innovations, right? And these curves will eventually flatten out. But surprisingly, this curve does never reach 0, means that there's a portion of adopters who keep the current version and never adopt newer versions of the same app. Okay, so here we find another new category of adopters. So we can call them preservers of an innovation. So from our data, we can observe 3 new types of adopters. One is immediate adopters. These are recurrent adopters who promptly adopt a new innovation of the technology upon its release. And the second type is preservers. These are adopters of one innovation of the technology who do not adopt newer innovation. And the third type is retro adopters. We found from our data set that although most users eventually adopt newer versions of the technology of the apps, some users decide to roll back to earlier version after adopting a new one. And actually, these new adopter categories represent a significant portion of users in our data set. We found that about 57% of versions are made up of more than 20% in immediate adopters, And about 90% of versions have more than 20% preservers, and about 0.5% of versions have more than 20% retro adapters. And when we consider the versions of an app as a whole, when we look at the cumulative adapters of an app, we can see the release of new versions actually brings new users, new adapters to this app. And we can see the interactions between the versions, like we can see part of the adapters of an existing version, they will switch to newer versions, right? And we can see there are significant variations between different versions of an app. So our next part of this work is to predict, to understand if the individual adoption decisions is predictable, right? As we mentioned before, in existing work, there's lack of the user level behaviors, right? So since we have this kind of data, we are interested in understanding whether the adoption decisions of individual adopters is predictable. And in this specific context of mobile apps, the user adoption of the latest version is actually very important for developers' revenue and user safety. And we have found from the data that the adoption decisions can vary per individual user and individual innovation. So we form this as a standard prediction task. So that is the user's behavior of adopting a recurrent innovation predictable? And if yes, what kind of factors could explain the decision of adoption? These are our features. So the first two dimensions are actually from the traditional theory. So one is the properties of the app, which corresponds to properties of the innovation in theory. And the second is the characteristics of the user, which corresponds to characteristics of the adopter in the theory. So we proposed a comprehensive set of features to describe these two dimensions. And the third dimension is the user's interaction with the target app, including its previous versions, which is not actually covered by existing series because existing work hasn't considered, the successive versions of innovations. So here we measure the user interaction with the target app using as many features as we can measured by our dataset. So as that is a very standard prediction task, we just briefly report the model for performance here, and you can refer to our paper for the details. So for these two tasks, we can see standard machine learning models like GBDT can achieve decent prediction performance in terms of adopt or not prediction and the time to adopt prediction. And furthermore, we did the feature interpretation to understand what kind of factors contribute to the adoption decision of individuals. Okay. To summarize, we observed novel and intriguing patterns in the adoption curves of recurrent innovations that the single and successive innovation adoption theory cannot explain. And we found 3 new types of adapters to be added into the diffusion of innovation series. And we proved that standard machine learning models are able to predict users' decision to adopt a new version of an app. And we also proposed some important aspects to consider to potentially improve the engagement and adoption of individual users. And our work also provides a lot of implications. So in terms of practical implications, our work provides a unique lens for user profiling, right? So app developers can prioritize their development strategy according to, so to meet the demands of different user groups. And being able to predict whether and when a user will adopt a specific version can help the developers of apps optimize their development strategies. And finally, the interpretation of features by our prediction models can provide valuable insights for developers, helping them to increase adoption and in-app engagement rates. And we also provide some theoretical implications. So first of all, we introduce the term recurrent innovations, right, to better describe the innovations nowadays, especially in the digital era. And we observe distinct diffusion processes, and we discovered this kind of patterns with the testbed of app versions as one of the most typical recurrent innovations. And we expect more detailed analysis of adoption patterns to expect when data is available, right? More data about the users, more data about the distribution channels, something like that. And we call for more research efforts to generalize the recurrent innovations to different fields and extend the theory, especially in the digital era or the AI era. And we also point out some future research directions. So first of all, application to different domains, different specific domains. And according to the elements pointed out by the traditional theory, we need more research to study the characteristics of the innovators, characteristics of the adopters, and the different modern communication channels nowadays, and the diffusion in social networks. And we also noticed that the innovations, actually, they have different relationships with each other, such as competition and collaboration. So new data and new research efforts is needed to study these new relationships. And of course, our work has its own limitations as we focus on just one kind of recurrent innovation. The results and findings cannot be directly generalized to other domains. But we provide an initial understanding of the recurrent innovations and how to understand the diffusion patterns. And the dataset selection may introduce some bias and limit pattern understanding because of the selection strategy of the apps based on our dataset, and some meta information which is actually very important and not available in the dataset. So there could be more detailed, more in-depth analysis when such information is available. All right, that's all for my presentation today, and I'm happy to take any questions.
Okay, I think we can take like one question for that, and then we can have others, like you guys get a chance to discuss and find each other for other questions for talks earlier that you didn't get to ask. So.
Thanks for the great talk. I was wondering maybe if you could maybe tell us a little bit about the features that were most predictive, and if you found any sort of interesting things there, or does everything kind of align with what you would expect based on theory, or what kind of insights you get from the prediction exercise?
You mean any interesting findings from the interpretation of features?
Yeah, like the ones that were most predictive of adoptions. Yeah.
Okay, let me yeah, so I think from our experiment, how users interact with the previous versions of the app is very important in the prediction task. Like how many days they use the app in the past certain period of time, like the past 2 weeks or the last week, and how they adopt the previous versions of the app. Yeah.
Thank you.
Thank you.
Are we at? I think there was in the third talk, there was one more. Well, okay, let's thank the speaker and then.
Thank you, everyone.
Are there any questions for any of the other speakers in this session? Because I know we went a bit quickly through part. Yes.
I want to follow up with the media bias check comments. Basically, you outsource it to media bias check, but they're, as far as I understand, manually fact checking articles, right? And so in real time, if there is an ad published, if somebody is applying for ad approval, then if there's no fact check on them, media bias check would not have captured it, right? And also, as far as I understand, media bias check ratings are domain level, not article level, right? So if there's one misinformation article, maybe they don't rate it as misinformation website, but it's still, yeah.
Yeah, that is correct. We discuss it in real time, but this is the job of the ad networks. You if something any information after it's been approved should be funded and demonetized now, right? So, but it was a measurement study, so don't really have real time to it. Now, regarding the article versus the domain question, they evaluate articles and then attribute the label to the entire domain. So there are some cases where domains can be classified as mixed transport units because they have only one or two paid articles. But my understanding is that their methodology evaluates the bias, these websites, and the sources that we use, if they're open to changing things. And so, yeah.
I think it's still interesting, even for a measurement paper, it would be still interesting to see what the content level misinformation, the effect of it on the ad placement, yeah. Not just at the domain level, but yeah.
Okay, let's thank all the speakers again. Great job. And we have lunch, I guess, in the main area.